Assalamu alaikum wa rahmatullah. Hello guys. Today we will talk about convolution neural networks. It is one of the greatest and the fundamental neural networks in deep learning. I have prepared a presentation, so let's go to the presentation. Just a moment. Let's play. Okay. So I will go to the first slide. Convolution networks. Chapter 9. So I have read chapter 9 and I created the presentation which briefly explains what is written in that chapter 9 and what is convolution networks. So basically, simply speaking, convolution networks are simply neural networks that uses convolution operation instead of general matrix multiplication at least in one of their layers. That's all. If the networks use convolution in at least in one of their layers, it means they are convolution networks. That's simple. So what is convolution operation then? So convolution operation is a mathematical operations which uses two functions to create the third function. So convolution operation, we can say in our case it is applying kernel to the input and shifting to the right in the input, shifting the positions of the kernel to the input. So if you look to the animation, you can see here clearly that we are applying this kernel of 3 to 3 grid to the image of the 7 to 7, and here we are calculating the convolution operation, and it results as another smaller grid, smaller representation. So that's how convolution operation means. Let's talk about motivation behind these convolution networks. The first motivation is sparse interactions. If you look to this graph, you can see that in the first top one, that in order to form the S3, so x2, x3 and x4 affects to the creation of S3. However, if you look to the bottom graph here, we can see that this S3 is created by using all the previous nodes, like from x1 to x5. So here you can see that in order to form this S3, we are using less computation, so we are omitting this x1 and x5 to compute this x3, and the same for x1, x2, s1, s2, s3, s4, s5, which means we are spending less computation and it is faster. So this is one motivation of why CNN are successful or why they are effective. Next thing is parameter sharing. So here, if you assume that this black arrow is parameter of central 3-element kernel, so which means that it shares from each node to another node, from x5 to s3, s5, from x1 to s1. However, in traditional networks, we don't have this parameter sharing. Instead, we use only once and unique, and we just use one time the unique parameter for that. For example, x3 to s3. So this parameter sharing is another motivation for CNNs. The last thing, another motivation, is equivariant representations. So a function fx is equivalent to the function g if f of g of x is equal to g of f of x, which means that if we apply some kind of transformation to I, and then if we apply the convolution after that to the I, we will result in the same result as if we apply convolution first to the I and then apply the transformation. So that's how CNN works. So the order doesn't matter for CNN. And in parameter sharing, one more thing is that we are using one parameter for many times, which means that it is also good for computation, less computation. Next thing is pooling. So pooling is one of the important part of convolution networks. So convolution layer actually consists of 3 stages. So first stage is convolution stage, where we apply the convolution operation. Next stage is detector stage, where we apply the activation function to the resulting matrix or vector. And after that, after applying this nonlinearity or this activation function, we are using pooling. So here pooling means getting something from this resulting result from something. So we have max pooling, for example. In max pooling, we have the given array of values, and we get the maximum out of that array. How pooling helps actually? So pooling helps to make the representation approximately invariant to small translation of the input. Invariant means that if we translate the input by a small amount, or if we change the input by small amount, the value in the pooling stage will not change, will remain. It means that, for example, it helps in the logic that when we have to do determining whether the image contains a phase, we will not know the location of eyes in pixel perfect accurate. We just need to know that there is an eye on the left side of the face, and there is an eye on the right side of the face. So pooling helps us to do the second one, to just let us know that there is eye on the left side of the face and there is eye on the right side of the face. That's how pooling works. And there are many different pooling strategies, maybe mean pooling, max pooling, etc. You can also create your own pooling. So that's how pooling works, that's how convolution layer actually works. And the convolution gives us assumption. The first assumption is that the objects can appear anywhere in the image, and the convolution, this pooling and convolution, follow this. So for convolution and pooling, it doesn't matter where the object in the image, they can find that, and their algorithm is working in the same prior in this assumption. Second assumption is that the pixels, neighborhood pixels, affect to the calculation compared to the pixels located far from it. So which means that, for example, if we want to find object in the center of the image, we don't need necessarily look to the pixel on the edge, on the right top corner of the pixel of the image. And the third assumption is that the complex objects consist of small patterns or simple patterns. For example, if we want to detect or recognize human, what we need to do is that convolution will consider to collect small patterns like legs, egg, head, and etc. So this way, convolution and pooling provides this strong prior about our data. And let's talk about these basic convolution functions. So we have locally connected layers, we have tiled convolution, we have standard convolution, and then we have fully connected layers. Fully connected layers, we have discovered it is feed-forward networks, where in order to create this S1, S2, all previous nodes are needed to calculate it, which means it is expensive. But in convolution, we don't do like that. We apply the kernel. So kernel, maybe it is A and B and C and D, So we can apply two kernels, we can apply one kernel, or we can apply these locally connected layers where we have unique parameters for each calculation. So this is the different types of convolution functions. So in tailored convolution, we have here two kernels. First is A and B, second is C and D, and they are applied after each one in sequence. In standard convolution, we apply just one kernel throughout this calculation. And this is effective, this is less expensive to do, and it is fast. Let's talk about structured outputs. So convolution neural networks are not only used for image classifications like classifies dog and cat and etc. They can also be used in image segmentation. For example, we can tell the convolution network to give us the output in different format. For example, to give the output in the special tensor S, where each pixel is given the probability to which class it belongs. By getting that one, we can simply represent or overlay that probability on our image. For example, here, the same convolution network trained on the data, it gives us the probability that certain pixels belongs to that it is car, that it is human, that it is flower, or that it's bicycle, etc. So we can change the strategy objective of the output of the CNN also. If you ask me what kind of data set or data types CNN can be applied, CNN can be applied to any data type which we can represent as grids. It can be 1D, 2D, 3D, it can be image, it can be audio, it can be video, it can be colored image, and etc. And another key feature of CNN is that CNN can be applied to the input with different sizes. For example, in traditional networks, one disadvantage of traditional network is that, for example, if I give to traditional models the image with size of 480 to 640, I should always keep giving the same input. However, in CNN, I can change the strategy, because in CNN logic, as you know, we can apply these kernels to the input, and we can change the kernel size or change the input size so that we will receive the same size as our output of CNN calculation. So that's the benefit of CNN. And another thing is that random and unsupervised features. Back in 2007 to 2013, when we had lack of computation and lack of this hardware development, scientists wanted to train this CNN in different way instead of using this simple supervised approach of training. Because supervised approach of training was very expensive for that time to compute, so that scientists discovered another ways of training the models. So first thing is initializing the kernels of the CNN randomly, which was at that time working good, or designing these kernels by hand, or to use unsupervised criterion, to use unsupervised to find these kernels. However, after some time, with development of these hardwares and with these GPUs, the best approach becomes just supervised learning. Just using this backpropagation and training these CNNs becomes best and realistic approach. So that's about another topic. And another topic I want to talk is neuroscientific basis for convolution networks. So convolution networks are how can I say, came from the neuroscience abstraction, and it basically comes from, we can say, the experiment in 1959 the Hubel and Wiesel did on the cat, how cat's brain simulate when the cat is shown different images or different objects. And by using that discovery, or by using that kind of analysis of that experiment, the CNN also kind of implemented in that way. So this one become one of the greatest, how can I say, great discovery in neuroscience, and it also pushed that convolution networks are the way how our brain works. And lastly, let's talk about the history of deep learning and how these convolution networks affected to the deep learning. So convolution networks have played an important role in the history of deep learning. They are a key example of successful application of insights obtained by studying the brain to machine learning application. They were also some of the first deep models to perform well, long before arbitrary deep models were considered viable. Convolution networks are also some of the first neural networks to solve important commercial applications and remain at the forefront of the commercial application of deep learning today. And convolution neural networks are also one of the first successful working deep networks trained on backpropagation. And one more thing is that at that time convolution become successful because that it consumes less computation, and at that time it is generally believed that convolution neural networks are better than fully connected layers. But now with good hardwares, when scientists train these fully connected layers, they also perform well now. We proved that that fully connected layers can perform well as convolution networks, but that fully connected layers needs more time and they are more expensive to train. So that at that time in the history, scientists couldn't prove that fully connected layers are good. But with convolution networks, as you know here, that convolution networks uses less computation, and they are in that case they become one of the first working with backpropagation, one of the successful deep learning models. So that's it for today, guys. That's it. That's it for today, guys. Thank you very much for your time. If you have questions, ask in comments below. So this is briefly about convolution neural networks in chapter 9 in deep learning book of Ian Goodfellow and etc. et al. So thank you for your time. Take care. Happy coding. Have a good day. Bye bye.